So we're going to continue with solving by elimination just like we did yesterday. And again, we're not ready to move into where we're actually changing one or two of the equations. We're going to save that for tomorrow. Alright? But today we're going to be taking a look at our special cases and differentiating what is a one solution problem, what is a no solution problem, and what is an infinitely many solution problem. And here's the nice part. It really is going to appear the same way it did with substitution. Okay? So when we did substitution and we came up with our quote-unquote special cases, we solved for the variable, we plugged it in, we simplified, and the variable was eliminated. Actually, in fact, both of them were eliminated, and that's what caused it to either be in all real numbers, or sorry, not all real numbers, infinitely many solutions, or it showed that it was a no solution. Okay? Nice part is it's the exact same idea here. Now here's what we want to keep in mind. If not both of your variables are eliminated, meaning there's still one variable left in the work, how many solutions does that mean it has? It has one. Okay? So the only time that we have a special case is if all of the variables have been eliminated completely. Okay? So let's take a look at example 4a. What we talked about yesterday was we're looking at the coefficients of the variables. Start with the x's, and if we need to, move on to the y's. And we're looking for the same number that's in front of both of those. We don't care if they're positive or negative, but we're looking for the same number in front. So Megan, when we look at example 4a, and we look at the x's, do we have the same number in front of both of them? Yes, we do. Okay? Again, the fact that one's 10 and negative 10 is not significant at this point, but we have what we want where we have a 10 and a 10 in front of those x's. Now our job is to do one operation, either add or subtract, to get rid of those. Now we actually care about the signs. The top one is a negative 10, the bottom one is a positive 10. How are we going to eliminate those, adding or subtracting? We're going to need to add. So what we're going to do here is we're going to add down each column and simplify it. Again, as I talked about the other day, or earlier today, make sure you show me what operation you're doing. Okay? So we're going to start adding down here. So on that left-hand side, as I add my x columns together, negative 10 plus 10 is 0. Those are eliminated. Okay? Then I go to my y's. What's 6 plus negative 6? It's also 0. So by adding these two together, I eliminated my x's, which is what we wanted to do, but we also haven't ended up eliminating our y's, and that leaves us with 0 over there on the left-hand side. Now again, as soon as we know that both variables are eliminated, we know this is a special case. Now we don't know which one it is yet, because it depends on what the other side of the equation is, but we know that this is either infinitely many or no solution. So now we travel over to the other side, and we take 6 and negative 12, we add those two together and get negative 6. So remember, the way that we determine no solution versus infinitely many is by what statement is left. So is the statement you are left with here, Molnick, true or false? It's false. 0 does not equal negative 6. So when it's false and 0 does not equal negative 6, what do we put? We put no solution. And once you're left with a no solution, there is no second part of the problem, plug it back in and find the other half of it. That's it. That's your no solution. So I'll be honest, solving special cases by elimination, when you've already got your variables matched up the way you want them to, it's really a pretty quick process. Now again, will these variables always be matched up like we want them to be? No. That's what we're going to start taking a look at tomorrow in section 6.4. Okay? So now let's slide down to example 4b. We're going to solve this equation by elimination as well, or system by elimination as well. Okay? So again, I've just begun with the first variable. So we're taking a look at our x's. Adriana, do we have the same number in front of our two x's? Good. So now we can go straight to addition or subtraction. Briley, in order to get rid of those x's, do we want to add or subtract those? We want to subtract them. Okay? Again, I'm going to treat this as a subtraction problem. We discussed last class period other options that you have. You can add opposites. You can multiply the second equation by -1, whatever works for you. But now we're going to go ahead and subtract through our columns. So we already know that our 6x minus 6x should give us 0, because if it didn't, then we chose the wrong operation. Okay? If we take 3y minus 3y, though, we're going to be left with 0. So again, in this particular problem, the variables have completely been eliminated. And if both of them have been eliminated, then we know it's a special case. We don't know what that special case is until we get to the other side. What's 27 minus 27? It's now 0 as well. So in the previous problem, we put no solution because the statement that you were left with was not true. 0 does not equal negative 6. This statement is true, though. 0 is equal to 0. So Evan, what do we need to put if 0 is equal to 0? Close. We want to put, Graceland, infinitely many solutions. Now again, why is this different than all real numbers? All real numbers implies you can plug anything in that you want, and it's going to make the system true. Okay? 0, 0 would then be a solution. And if I plug 0, 0 in, is that a solution? No. So, there are more than one answer. In fact, there's an infinite number of answers. But remember, going back to graphing, trying to keep this all connected here, we're only talking about values that are on this line. So 0, 0 is not a solution. 0, 9 is, though. Plug 0 in for x, plug 9 in for y, that is a solution. So because there's only select ones that are, that's why we're putting infinitely many rather than all real numbers. Harley, question? Well, you'd have to show that, yeah. No, this is it. Show me if you're adding or subtracting. Okay, because you're going to copy down the problem, you're going to add or subtract them. So what I have here is what I would expect to see for work. All right, now let's slide down to example 4C. So in 4C, we're looking at, do we have an equation or a variable with the same number in front of it? Okay, Caleb, what would we say? Do we have a variable that's got the same number in front of it? Yes. All right, which variable? The y's. So here's what we need to do. We need to get rid of these so we can eliminate them. So what are we going to do? Are we going to add or subtract in this problem? We're going to subtract. Okay? Now, this is where you need to be careful because there's a lot of people who assume the answer is going to be this, and so they make it fit what they need to. You need to show all of this work. So start on the left-hand side. What is 3 minus negative 2? 5. So this should be 5x. Right off the bat, if I have 5x, what do I know? There's one solution to this problem. Okay? What's 8y minus 8y? 0. That has been eliminated. What is negative 16 minus a negative 16? It's 0. Now, a lot of times, people will go, okay, you got 0, this has had a bunch of stuff cancel out. This should be no solution. No. If you still have a variable left, you still have one answer, we said. So you still need to complete this and solve for x and y. What are we going to do to solve for x? Divide each side by 5. And when we divide each side by 5, we get x to be equal to 0. That's part of my one answer. What do we still need to find? You still need to find y. So to find y, you're going to need to take this value of x and plug it back into one of these two equations. 3 times 0 plus 8y equals a negative 16. 3 times 0, of course, is 0. And 0 plus 8y is still just 8y. Divide each side here by 8, and y turns out to be equal to negative 2. Okay, if I plug that back in, since I used the first equation to find y, I plug that back into my second one. Negative 2 times 0 is still going to be 0. 8 times negative 2 is negative 16. 0 plus negative 16 is negative 16. Alright, questions on these? I always throw one in where it's no solution, infinitely many, and then a 0 just so we understand that this means I have one solution. Okay? Alright? But now I want to flip it over to the back. We have a story problem. If I remember correctly, this one is a little challenging. Yep, it is. I want to practice this today, and then tomorrow our opener will be similar to what we're going to do here. Okay? So a little bit of background, because I didn't put 2 of these on here, I only put 1, but these are really the exact same types of problems. Okay? So let's read through this one first, talk about it, and then I'll talk about another scenario that we have. So then it says that a riverboat travels 28 miles upstream in 7 hours. Okay? And it travels 28 miles downstream in 5 hours. Alright, let's pause there and think about that for a minute. This is something that I assume we know, but we don't always know, so this is what I want to talk about. What does it mean when you travel upstream? There's a difference between upstream and downstream, and we need to know the difference here. Okay, against the flow of water. If I am traveling upstream, I am going against the current. Okay, and if I'm traveling downstream, I'm traveling with the current. Okay, so my example that I always use, we live next to the Mississippi. Okay, if I started in Davenport and I traveled to Dubuque, I am going upstream. Okay, when I travel to the north on the Mississippi, I'm going upstream most of the time. Okay, when I travel from Dubuque to Davenport, I'm going downstream. So when it makes sense, if I have a boat that can go the same speed, okay, it's always traveling 10 miles an hour. When I go upstream, am I actually going to be traveling 10 miles an hour? No, because the current's going to slow me down. When I travel downstream, am I actually going to be traveling 10 miles an hour? No, because the current's going to push me and go faster, and I'm actually going to be going faster than 10 miles an hour. So anytime that you're on a river that's got a current to it, you have this in play. Okay? So this is the scenario that's being described, because this riverboat took 7 miles to go 28 hours, or 28 miles, but then when it flipped around, it only took 5 hours to come back. Because when it was going upstream, it was going slower than when it was coming downstream. Okay, now, not many of you probably have ever, and how many of you have been on a riverboat before? There you go. A couple of you have. Now, here's another scenario many of you probably are aware of. How many of you have ridden on an airplane before? There you go. Where would this come in with airplanes? The airflow. When you travel on an airplane, you either have a tailwind or a headwind. What would a headwind tell us? Is it making you go faster or slower? Slower. Okay? But if you have a tailwind, you're actually going faster. So you may or may not have ever played around with this, but like if you were to fly from Cedar Rapids to Denver, and then turn around and fly from Denver to Cedar Rapids, one of those trips is usually shorter than the other, time-wise. You can be on the exact same plane, they can travel the exact same speed in the airplane, but one is faster and one is slower. When I travel from Cedar Rapids to Denver, it takes me longer than when I travel from Denver to Cedar Rapids. Why? Because the airflow. The air usually blows from the west to the east, so when I'm traveling to the west, I have a headwind, and when I travel to the east, I have a tailwind. These are all things that come into play. So when we see these problems, we're thinking of a riverboat, and upstream and downstream, we're thinking of an airplane with a headwind and a tailwind. Okay, those are things that we need to know. Now, rereading this problem. A riverboat travels 20 miles upstream in 7 hours. It travels 20 miles downstream in 5 hours. The speed of the current remains the same during the travel upstream and downstream. Find the average speed of the boat in still water. So if I were to take that riverboat and put it into a pond, how fast could it go? Okay? And also find the speed of the current. How fast does that current go? Okay? That's our job here. And I'll be honest, this is not just a quick, one easy step and we're done problem. So this is actually a multi-step problem here. And we're going to begin, before we do a system of equations, okay, we're going to begin with this. We need to figure out how fast the boat was going upstream. And we also need to figure out how fast the boat was going downstream. Okay? And in order to do that, we need to use a formula that we were introduced to last year, and probably several years even before that. Our D equals R times T formula. Can somebody guess what this formula tells us? Miles. Oh. Distance equals rate times time. You know how fast you're going and you know how long you've gone, you can determine how far you've gone. If I'm in a car that's traveling 60 miles an hour for 3 hours, that means I've traveled 180 miles, right? We all used our distance rate time formula before, I'm sure. Okay, we probably just haven't ever thought about it as D equals R times T. So let's use this to determine our two things. So we have upstream. Okay, when we traveled upstream, how far did we go? 28 miles. Do we know how fast we were going? No. So our R stays as an R. Do we know how long it took us? 7 hours. So if I plug this into D equals R times T, I get this, correct? So how fast was the boat going upstream? 4 miles per hour. Divide each side by 7, and R should equal 4. Okay? Now, we have downstream. When we traveled downstream, how far did the boat go? 28 miles still. How fast was it going? We don't know. How long did it take? 5 hours. So can you determine how fast the boat was going? Yep. Divide each side by 5, and what's R turn out to be? What's that? 5.6. So, when we were going upstream, the boat was traveling 4 miles an hour. When we're coming downstream, the boat was traveling 5.6 miles per hour. Okay? We should be able to use this to help set up and solve a system of equations. Okay? So does everybody have this copy down so I can erase it? Okay. Now, two things they ask us to find. What do they ask us to find? Speed of the boat and speed of the current. Okay. I'm not going to use S because both of them are speeds. So I'm going to go with B as the speed of the boat. And I'm going to go with C as the speed of the current. Now, two equations I'm going to set up here. And one of them is for our upstream and one of them is for our downstream. And together it's going to create a system of equations for us. So when I went upstream, the boat is traveling some speed. I don't know how fast it's going, but it's traveling at B miles per hour right now. Does everyone agree with that? Now when it's traveling up speed, the current, is it making the boat go faster or slower? Makes it go slower. So what's happening to the speed of the boat? It's subtracting what? Subtracting C from that. Because it's telling me that I'm going B miles per hour, but I'm being slowed down by whatever the current is. Now, this should represent the speed of the actual boat. How fast was the boat traveling upstream? 4 miles an hour. So if I take the speed of the boat, subtract my current, I'm going to get my actual speed, which is 4 miles per hour. Okay, now what about downstream? How fast did the boat start by going? B miles an hour. Now, was that current helping or hurting its speed? It was helping. So what was it doing to B? It was adding C. And when we added C to that, what did we get? 5.6, because that's how fast it was going downstream. Here is your system. Now let's solve it. Now here's the beauty of this problem. What would you do to get rid of your B's? Subtract. What would you do to get rid of your C's? You'd add. You can do either one. I don't care. Now, most people, because they have a preference, like to add. So if you're going to add these down, you're going to take B plus B, which is 2B. You're going to take negative C plus C, which is 0. That's been eliminated. And you're going to take 4 plus 5.6, which turns out to be 9.6. And if you divide each side by 2, B turns out to be 4.8. So what did we just find there? That's the speed of the boat. In still water, the speed of that riverboat is 4.8 miles per hour. Now, we still need to find the speed of the current. Take that and plug it into one of your two equations. Does it matter which one? No. Okay? So I'm going to take it and plug it into the bottom one. 4.8 plus C equals 5.6. If I subtract 4.8 from both sides, then C is equal to 0.8. What did we just find out there? That's the speed of the current. And you should be able to check that by plugging it back into the top one. If we took 4.8, which is the speed of the boat, subtracted 0.8, which is the speed of the current, that's the resulting 4 miles per hour that it traveled upstream. Lots of layers to this problem, okay? And he's no longer in our class right now, but this is the example that Mr. McCann used to like the best, because he actually served in the Navy. And this was the problems they'd have to do to determine how fast the boat was going. When they were on the Mississippi River, traveling upstream and downstream, you would have two drastically different amounts of times that it would take. Because in one way the current was helping, and in one way the current was hurting. And so they would be able to use a system of equations just like this to determine how long is it going to take, or how fast are we moving, or how fast is the current. They can do all of those different types of things. Okay? All right. Questions that you have on this example? I'll be honest, example 4, probably not anything too challenging. This type of problem is a big part of what we wanted to make sure we took a look at today. Again, we'll practice these for our next couple of days worth of openers with airplanes and boats and everything else, but this is something that I wanted you to be prepared for. Alright, so your homework tonight is going to be a worksheet, so you can just keep this in your notes, and I'll grab the worksheet here and get it for you, hand it out in just a moment.